Have you ever wondered how electrons are organized in an atom and why this arrangement matters? Well, today we're going to explore the fascinating world of electronic configuration. This term may sound a bit intimidating, but it's simply the distribution of electrons of an atom or molecule in atomic or molecular orbitals. It's like the seating arrangement at a concert, but for electrons. Knowing how these electrons arrange themselves is crucial to understanding a lot about our world. It's the key to unlocking the mysteries of chemical reactions and the properties of elements. From the oxygen we breathe to the gold in our jewelry, electronic configuration plays a significant role. So why does this matter? Because understanding electronic configuration helps us understand how the universe works, from the smallest atom to the largest galaxy. Now that we've established what electronic configuration is, let's delve deeper into how it works. The arrangement of electrons in an atom isn't random, it follows certain rules. Do you know what they are? Let's dive into the three main principles that govern electronic configuration: the Aufbau principle, the Pauli exclusion principle, and Hund's rule. First up, the Aufbau principle. This principle is all about building up. It states that electrons occupy the lowest energy level first, before moving to higher energy levels. Picture a hotel. Guests would prefer to stay on the lower floors before the upper floors, right? Similarly, electrons prefer to occupy lower energy orbitals before moving up. Now let's discuss the Pauli exclusion principle. This principle dictates that no two electrons in an atom can have the same set of 4 quantum numbers, which are essentially the addresses of electrons. In other words, each electron in an atom has a unique identity. It's like having a unique passport number. No two people can have the same one. Finally, we have Hund's rule. This rule states that electrons will singly occupy all the orbitals in a sublevel before they start pairing up. Think of it as people taking seats on a bus. They'll fill all the available rows with one person before anyone starts sitting next to someone else. These principles might seem a little daunting at first, but they're just rules that electrons follow to find their seats or orbitals in an atom. And just like how knowing the seating arrangement in a theater can enhance your movie experience, understanding these principles can give you a deeper insight into the fascinating world of atoms. Remember, the Aufbau principle is about building up from lower to higher energy levels. The Pauli exclusion principle ensures each electron has a unique identity, and Hund's rule is all about singly occupying orbitals before pairing up. These principles might sound complex, but they are fundamental to understanding how electrons occupy orbitals. Ever wondered why the periodic table is structured the way it is? Let's delve into the fascinating world of the periodic table and the electronic configuration of atoms. You see, the periodic table isn't just a random collection of elements, it's a carefully crafted map reflecting the very nature of elements and their atoms. Every element in the periodic table has its unique atomic structure. The atomic number tells us the number of protons in an atom's nucleus. But what's equally intriguing is how the electrons are arranged around this nucleus. This arrangement, my friends, is what we call the electronic configuration. Now, let's take a closer look at the periodic table. Notice the vertical columns? These are called groups. Elements in the same group share a unique characteristic. They have the same number of electrons in their outermost shell, also known as valence electrons. These valence electrons determine how an element will behave chemically. So, elements in the same group have similar chemical properties because they share the same number of valence electrons. Take the noble gases, for instance, located in group 18. These elements are remarkably stable and unreactive. Why? Because their outermost shell is full. They have no room for more electrons, and so they don't tend to engage in chemical reactions. On the other hand, the alkali metals in group 1 are quite the opposite. With just one electron in their outermost shell, they're eager to give it away, making them highly reactive. So you see, the periodic table isn't just about listing elements, it's a sophisticated map that gives us insights into the electronic configurations of atoms and their consequent chemical behaviors. And just like that, the seemingly complex structure of the periodic table becomes a bit more comprehensible, a bit more intriguing. Each group, each period, each block unravels a story about the elements and their electrons. So, the periodic table is not just a list of elements, it's a map of electronic configurations. Let's put theory into practice, shall we? It's time to delve into some examples of electronic configuration. Let's start simple, with hydrogen, the first element on the periodic table. Hydrogen has only one electron, so its electronic configuration is simply 1s1. This means that its single electron resides in the first energy level, or shell, in the s subshell. Moving on to helium, the second element on the periodic table. It has 2 electrons. Both of these electrons fit into the first shell, in the s subshell. Thus, the electronic configuration of helium is 1s2. Now, let's step up the complexity a bit. Consider lithium, the third element. Lithium has 3 electrons. The first 2 fill up the s subshell of the first shell, just like helium. But the third electron, it moves on to the second shell, once again in the s subshell. So, the electronic configuration of lithium is 1s22s1. It's important to remember that each shell is divided into subshells, and each subshell can hold only a certain number of electrons. The s subshell can hold 2, p can hold 6, d can hold 10, and f can hold 14. The shells fill up in a specific order, dictated by the energy levels of the subshells. Let's take a look at an element a bit further down the periodic table, say carbon. Carbon has 6 electrons. The first 2 fill up the s subshell of the first shell, the next 2 fill up the s subshell of the second shell, and the final 2 go into the p subshell of the second shell. Therefore, the electronic configuration of carbon is 1s22s22p2. Remember, the key to figuring out the electronic configuration of any element is understanding the principles we discussed earlier, the distribution of electrons among the shells and subshells, and the order in which they fill up. Once you've got that down, it's just a matter of counting up the electrons. With practice, figuring out the electronic configuration of any element becomes a breeze. So why should we care about electronic configuration? Well, the importance of electronic configuration stretches far and wide, infiltrating various fields of study and practice. It is a fundamental concept that provides a deeper understanding of how the atomic world functions, and its applications are truly fascinating. Take chemistry, for instance. Electronic configuration forms the bedrock of our understanding of chemical reactions. It helps us predict how different elements will interact with each other. This understanding is key in predicting the products of a chemical reaction, which is essentially the bread and butter of chemistry. Moving on to material science, here's where things get really interesting. The electronic configuration of an element can determine its physical properties. For example, it can tell us whether an element will be a good conductor of electricity or whether it will be malleable or brittle. This knowledge is powerful in designing and creating new materials with specific properties tailored for various applications. Now let's talk about a field that might surprise you: medicine. Yes, you heard that right. Electronic configuration plays a vital role in understanding the interaction between drugs and the human body at a molecular level. By understanding the electronic configuration of the atoms in a drug molecule, scientists can predict how the drug will interact with various cells and proteins in the body. This is an essential part of drug discovery and development. But electronic configuration isn't just about predicting reactions or creating new materials. It's about understanding the fundamental nature of our universe. By knowing how electrons are arranged in an atom, we can comprehend why elements behave the way they do. We can understand why gold is gold and why oxygen is essential for life. The world of atoms and electrons might be invisible to the naked eye, but understanding it opens up a universe of possibilities. So, let's keep exploring this fascinating world of electronic configuration together. Let's take a moment to recap what we've learned today. We embarked on a journey through the world of electronic configuration, starting with its basic principles. We discovered how electrons inhabit energy levels around an atom's nucleus, and how these configurations follow a predictable pattern, which is beautifully mirrored in the periodic table. We then delved into practical examples, demonstrating how to determine an element's electronic configuration. This not only fosters a deeper understanding of the atom's structure, but also aids in predicting chemical behavior and interactions. Lastly, we explored the importance and applications of electronic configuration. From determining chemical reactivity to predicting atomic behavior, the knowledge of electronic configuration is a powerful tool in the hands of scientists, chemists, and physicists alike. With this knowledge, you're now better equipped to understand the fascinating world of atoms and electrons. Keep exploring, and remember, science is always more than what meets the eye.